Thermochemistry starts the final section of CHE 120. In this section, we're going to look at the topic of thermodynamics. So this will help us answer the key why questions related to equilibrium. So why do certain reactions occur? Do reactions release energy or require energy? We had some information about the why of chemical reaction in kinetics, right? We have things about like activation energy, but when it comes to equilibrium, it turns out that you need the concepts of thermodynamics to really understand why a certain reaction favors products versus reactants. So that will involve here both the energy of a chemical reaction, which we'll look at in this section, and next the entropy, which we'll look at in the next set of notes. Energy is the starting point, which is difficult to define in a really precise way. One nice starting point, though, is that energy is the capacity to do work. So work has a nice, precise definition from physics. It's the application of a force across a distance, a nice example being the work you have to do to lift any sort of weight against the gravitational pull from the Earth. So anytime you're lifting things up into the air, you're doing work against that gravitational force. And we can calculate the amount of work that we would have to do to lift certain objects. And then we can say that if something is high in energy, that's something that has a great capacity to do work. So all of the chemical fuels in the space shuttle here have a lot of energy, and that means it has a lot of capacity to do work to lift the space shuttle up into the air. So with that little definition of energy to start with, the first law of thermodynamics deals with energy. You can think about what statement of that you've heard before. Okay, so some you've maybe heard before, right? One from maybe a lower level class might be this idea that energy is neither created or destroyed. That is a perfectly valid way of describing the first law of thermodynamics. Energy is only transformed from one form to another. A second way of saying it is that energy is conserved, so that in any process we can add up and see, okay, energy is going from some battery and it's being used to increase the kinetic energy of this Segway, say, or the car. And we can add up those little changes in energy. That's the really powerful thing about the first law of thermodynamics. So the first law then leads naturally to thinking about all the different types of transformations of energy that we can do. We can take chemical energy and convert it to electrical energy, as in a fuel cell. In coal or natural gas power plants, we have high energy chemicals, and we're able to release energy to heat up water into hot steam, and then convert that into electricity in a power plant. Again, all of the energetic changes in the human body and in plants also driven by this transformation of energy from one form to another. When we actually want to think about studying these changes in energy, we need to sort of precisely define all of our terms. So the first thing we always want to separate out is the system versus the surroundings. So the system here we're thinking about is this yellow solution, say. Then the whole rest of the universe we categorize as the surroundings. So system plus surroundings is equal to the whole universe. In general, there's a lot of different types of systems. Open systems exchange both matter and energy. We're going to mainly focus on closed systems that might exchange energy but not matter with the surroundings. And an even easier case to deal with is an isolated system that doesn't exchange matter or energy with the surroundings. When we have this more technical language about system and surroundings, the first law of thermodynamics can be stated then as the fact that the energy of the universe is constant, which means the energy of the system plus the energy of the surroundings is constant. As a result, then, any process that we do, because the energy of the universe is constant, we have delta energy of the system plus delta energy of the surroundings is equal to 0. Because overall there can't be any change in energy since it's conserved. So as a result, then, another way to write this is that delta E of the system is equal to negative delta E of the surroundings. Really, really powerful concept, because if I can say measure the energy change in the surroundings in some way, I can immediately say for certain, because energy is conserved, the energy change of the system had to be equal and opposite. So in chemistry, what we want to look at is the energy associated with chemical reactions. this is listed here as delta H. We'll explain why in a second, not delta E. But for delta H, remember that what we're thinking about is the energy change in a reaction. If we have a negative value there, it's an exothermic reaction, and we could think about heat as a product of the reaction. A positive value is endothermic, and heat is a reactant. So any of our reactions that are able to do useful work are going to have a negative delta H. So you think about, again, a reaction that releases a lot of heat, maybe burning methane. CH4 gas plus 2O2 goes to H2O plus CO2. This reaction releases a lot of heat. It has a very negative delta H, and that's why when we burn methane, we can make electricity or heat our water up when we're making something. These reactants are very high in energy, and therefore they have a high capacity to do work. We can release the energy. We can release energy by taking these reactants and turning them into lower energy, more stable products. The units associated with energy, the calorie is a nice unit. It's the amount of heat required to raise the temperature of a gram of water by 1 degree Celsius. The technical definition from 14.5 to 15.5 Celsius. The SI unit, though, is a joule, which is 1 kilogram meter squared per second squared is equal to 1 Newton meter. And the equivalence there is that 1 calorie is equal to 4.184 joules. If you ever think about a food calorie, that's really a kcal, or 1,000 of these normal calories. The next thing we want to think about with energy is heat and temperature. So these are all related concepts, but they are all distinct. So temperature is not energy, temperature is not heat. Temperature is going to tell us the direction that energy will flow as heat between two objects. So as you know from common experience, heat is going to flow from hot to cold. So if I have an object at 50 Celsius and an object at 20 Celsius, and I bring them into contact, what's going to happen is I'm going to have a flow of energy. I could view that as this arrow here with, we'll see the variable we use for heat is a Q. So there's going to be some amount of energy that flows from the hot object to the cold object. And let's say these are the exact same material at the exact same size, so maybe they end up at 35 degrees Celsius each after I bring them into contact here. And there's going to be some amount of energy transferred to cause this to take place. We can calculate these changes in energy and then use it to learn things about the chemical reactions, the properties of our materials. Heat's a very powerful way because when we transfer energy as heat, we get this temperature change. We can really measure these energy flows very precisely. Here's one approach then that uses that technique, the method of calorimetry. So what calorimetry is a method of measuring heat in a chemical reaction. The heat leaving our system is equal to the heat entering the surroundings. That's just the consequence of that first law of thermodynamics, that the change in energy of our system is equal to the negative change in energy of our surroundings. So the idea here in all of our calorimetry examples is we're going to have some chemical reaction happening. There's going to be a change in energy associated with that reaction, which might be difficult to measure. But because we have the surroundings here, in this case the surroundings is just a bunch of water, and in this case the same thing. The surroundings here is basically all the reaction that the water is taking place in. We can measure the heat of the reaction and measure the heat flow by measuring the temperature change of the surroundings, which is basically just pure water, which is easy to calculate, as we'll see in a second. So the way we actually calculate the amount of energy that flowed as heat into the surroundings in one of these experiments is using this equation. The heat flow when associated with the temperature change is equal to m, the mass, in usually grams, times Cs is the specific heat capacity. That is in units of joules per gram per Kelvin, or we can also write this as joules per gram degree Celsius. In the rest of the class, we need to make a really big distinction between a Kelvin and Celsius, because all the other equations in our class have something like this, e to the negative EA over RT. And there, since we've got the T multiplied by R, and it's just T by itself, it makes a very big difference if I plug in T in Kelvin versus in Celsius. But if you notice this equation that we have, it's a delta T that we care about. So since we care about delta T, whenever I do a delta T, I get the exact same answer in Kelvin and in Celsius. If I look at my example from the last slide, we went from 50 Celsius to 35 Celsius, then delta T is final minus initial, so 35 minus 50 is negative 15 degrees Celsius. If I convert both of those temperatures to Kelvin, I get 308 Kelvin minus 323 Kelvin, but the delta T is still negative 15 Kelvin because the Kelvin scale is the same size of unit as Celsius, just shifted by that 273.15 Kelvin, or 0.15 degrees. So these are exactly the same, and therefore as a consequence, in this one case, since it's a delta T, you can use Kelvin or degrees Celsius interchangeably, and you can think about your unit of specific heat capacity, joules per gram per Kelvin, as the exact same unit as joules per gram times degrees Celsius. Okay, then the equation here, M is just mass in grams. CS then is specific heat capacity, is a property of the material. So different materials are able to absorb a different amount of heat for the specific amount. So water here, you can notice in that table, has an incredibly high specific heat capacity compared to every other material on this table here. Metals, in many cases, absorb very, very little heat. So specific heat here, very low numbers for these metals. That means, according to this equation, right, if I have a small CS, then if I put a certain amount of heat into the system, I'm going to get a very large temperature change for a metal compared to for a non-metal. In the same way, since water stores so much energy when we heat it up, that sort of explains why oceans provide that nice moderating effect on temperature, because water stores so much energy as heat. Even once it gets to be, say, late in the fall, early in the winter, those oceans, which are warmer from the summer, are still retaining a lot of heat, and they're moderating the local climate because it takes a long time and a lot of energy for the water to lose all of that energy that it got put into it during the summer months. Okay, so try to get started on this first example problem on your own, and then I'll show the solution. Okay, we have aluminum, 15 grams, and we're given its specific heat capacity. Initial temperature, 20 degrees, that's our TI. We drop it into that water bath at 60 degrees, and eventually the aluminum's temperature reaches 60 degrees, so we can recognize that as the TF. The first question then is the heat transferred to or from the aluminum. In that case, the way we can solve that is, because we're given both the mass, the specific heat capacity, and we can see that we're going to know the temperature change, 60 minus 20, we're going to be able to apply that equation from the previous slide. So we can say Q of the aluminum is equal to the mass of the aluminum times the specific heat capacity of aluminum times the change in temperature of the aluminum. In this case, we have all those variables, so we can just sort of plug them in. The mass is 15 grams. The heat capacity is 0.900 joules per gram. Again, I wrote this as per gram Kelvin, but I'll switch that maybe here to degrees Celsius. Remember, those are interchangeable. In CS, just in these two cases, for CS and delta T, Celsius and Kelvin are interchangeable here. Then my delta T, final minus initial, is 60 was my final, minus 20 was my initial. And I get Q of the aluminum is equal to 540. The unit, though, is, you can just know it from the unit for energy, which is joules, but it will work out if we check. Grams here cancels the grams in the denominator, and the Celsius units here are going to cancel with this Celsius in the denominator, and we do get 540. So next we want to think about how much heat was transferred to or from the water bath. The water bath, we don't know anything about the amount of water in it. We don't know anything about its change in temperature. Our assumption is sort of here that it's so big that we basically keep it at exactly 60. Even that little bit of heat transferred to it from the aluminum doesn't really affect the water bath much. But we know that since the aluminum gained 540 joules of energy as heat, the water had to lose a corresponding amount. That's this idea that Q cis is equal to negative Q of the surroundings. And so if we view the system side as the aluminum, Q aluminum is equal to negative Q of the water. And so therefore Q of the water is just equal and opposite, negative 540 joules. And so that's always a step you have to be prepared to do in this part of the class, of just convert between systems and surroundings using the first law of thermodynamics, that any energy change is going to have, in this case, aluminum gained energy, the water lost an equal amount of energy. Remember that a positive number here means we're gaining energy, a negative number here means the water is losing energy. It's sending energy to the aluminum to heat it up. Here's another example here. This you can solve in that exact same way. A little bit more algebra involved. This honestly is one that, to save yourself some algebra steps, could be useful with, say, solver. But yeah, take a second and I will show the solution. The setup for a problem like this involves both of those two pieces, the Q equals mc delta T part, as well as the idea that heat or energy is neither gained nor destroyed, only sent from one place to the other. So the first idea, what is the final temperature of the iron? What is the final temperature of the water? The iron starts out hot, we drop it in the cold water. What's going to happen? Well, they start out at these very different temperatures, 75 and 20. We know that according to what happens when we mix things together, they're going to end up at the same final temperature. So even though they started at 75 and 20, they are going to end up at the same final temperature. How are they going to do that? Well, there's going to have to be a transfer of some amount of energy from the iron to the water. The natural way then to figure this out is to equate the energy transfer from the iron to the water to the energy that's gained by the water. A way to do that is to start from this equation. Q cis is equal to negative Q of the surroundings. So Q of the system, it doesn't really matter which side I'm going to pick the system. I'll just pick that as the iron. So I'll say Q of the iron is equal to negative Q of the water. Then for Q of the iron, I'm going to plug in the mass of the iron, the CS of the iron, and delta T of the iron. I'll just plug in that now. The delta T of my iron is, it started at 75, so that's my initial. It's final minus initial, so it's TF minus 75 is my delta T for the iron. Then on the other side of it, for the water, I'm going to have the mass of the water, the CS of the water, times the delta T for the water is going to be, it started at 20, and the final was TF, so TF minus 20. Now, if I plug in the rest of these values here, I can now actually get an equation I can solve. So I'll plug those in. The mass of the iron was how much? 32 grams. Times the iron heat capacity is 0.444 joules per gram degree Celsius. TF minus 75 is equal to, on the right hand side, I have 100 grams of water times that 4.184 joules per gram degree Celsius times TF minus 20. At this point, we've done actually all the science of the problem. All that's left is solving for TF. It isn't quadratic or anything. It's just a bunch of TFs that you have to sort of get everything to one side to solve. I'll show that on the next slide. But again, at this point, you're also free to plug that into solver, save some time of those algebraic manipulations. I'll show that one as well. Here's what solver looks like. I'm doing the minimal possible work, really just typing in the equation without doing any extra prep work because I don't have to. because I can do, both sides equals separate, I'm just doing, left-hand side equals right-hand side, remembering my negatives here. And in this case, the guess doesn't matter because it's a linear equation. It will always find the single correct solution, unlike with like a quadratic or something. And yeah, solve x, we get the final temperature of 21.79. If you don't want to use solver or don't have that calculator, you can just solve it normally, multiplying out the sort of prefixes here. Now I've got a TF on the left-hand side, a TF on the right-hand side. I have to keep expanding this. So I get 14.08 TF minus, this is 1056 when I multiply out the distribute to this term. On the other side, I get negative 418.4 TF minus, again, I have to do negative 20 times negative 418.2, which will give me positive 8368. Then the final algebra step here is collecting the constants on one side, collecting the TFs on the other. Because I have a negative over here for TF, I'm going to move that to the left and then move all my constants to the right-hand side. So when I do that, I get 14.08 plus 418.4 TF over here. And on the other hand side, I get 1056 plus 8368 on the right-hand side. The final result here, I have all my TFs on the left, my constant on the right, divide both sides by 432.48, and get that same final answer of 21.79 degrees Celsius with just a little bit more algebraic work there. Again, the algebra isn't difficult, just all sort of it's always a linear equation, no quadratic or anything, just move the t's over to one side, move the constants to another side, and get your final answer. If you're checking your answer, right, TF does always need to be between the two temperatures, so 75 and 20. When they come to equilibrium, it's always going to have to be more than 20 and less than 75. One of the times I was solving this problem earlier, I got 18 point something Celsius, and that I know can't be correct because it's less than 20, right? The water has to heat up. We have to end up with a temperature greater than 20 and less than 75. So if you find something like that, you can throw that answer out and look back and find your math error. Here are those same solutions, just shown on the slides from the notes for reference. And the solution here, again, if you had a different sort of solver, you would want to arrange it so that everything is equal to 0, just depending on which version of solver you have, whether you need to set one side equal to 0 or not. With that preliminary content about heat and the first law of thermodynamics out of the way, now we can look at studying the energetics of chemical reactions. Our starting point here is expanding on our energy accounting from the previous section. Now, if we view the system as this box, the surroundings as this, we know that any change in energy is going to occur via actually two methods. One, it can occur via heat, as we showed in the last section, but work is another way that we can change the energy of the systems. And a nice mathematical form of the first law of thermodynamics is that the change in any energy of our system, which like any change is final minus initial, is equal to the flow of energy as heat plus the work done on or by your system. And that's the only way the energy of our system can change, is if either heat flows to or from the surroundings or work is done, by the system or by the surroundings. Knowing the signs is really important. So if Q is positive, that's going to mean my energy is increasing, and that's the system absorbing heat. If Q is positive, that means the surroundings is doing work on my system. So if my system is some sort of gas and I squeeze the gas down, I'm doing work on the gas to increase its energy. And now the gas is compressed, and now maybe later on the gas has all this energy stored and we'll be able to release that energy and do work on the surroundings later. But that's the idea. We gain energy, that's a positive. We lose energy, that's a negative. So again, if the system transfers some energy to the surroundings as heat, that will be a negative sign for Q from the system's perspective. Just as before, we still have the same principle that delta E system is equal to negative delta E of the surroundings. And the same applies for each of those terms. Q of the system is equal to negative Q of the surroundings. All that same stuff that we looked at previously. Some additional terminology that's useful for thinking about thermodynamics is this idea of a state function. So a state function doesn't depend on the path taken between the initial and final states. This is really important because it gives us something solid to hold on to no matter how a reaction happens, whether it's in the human body or in a test tube or on an exoplanet. If I know the initial state and the final state, I'm going to know a lot of facts about that reaction. The energy change, the enthalpy change, some other variables we're going to define as well. So energy does have this property that it is just a function of state. So it is perfectly fair to say delta E is equal to E final minus E initial, which is incredibly powerful to let us study the energetics and thermodynamics of chemical reactions. Note that something like the distance traveled here depends a lot on the path. That's the same for heat and work in thermodynamics. We can do reactions in all sorts of different ways that have different amounts of heat and work, just like we can have different total elevation gain, different distance traveled to get from initial to final depending on the path, but the total change in altitude is always the same. So our energy diagrams are taking advantage of this fact. We've used these diagrams before. Energy of, say, my reactants here, energy of my products. In this case, my reactants are higher in energy, so energy is going to be released as heat when this reaction occurs. That's an exothermic reaction. The quantity of energy released is the final minus initial, and in this case, that's the energy of the water minus the energy of the starting materials. This downward arrow represents a negative change in energy because the change in energy of my system is negative when hydrogen and oxygen are converted into water, as in the Hindenburg exploding here. Hugely exothermic, a ton of energy released to the surroundings. This same process can happen in reverse when we do hydrolysis or water splitting here. We'll take water and use energy from a battery to split water into oxygen gas and hydrogen gas. That's the exact reverse process, and therefore we know that the energy we have to put in to make this process go is the exact same, equal and opposite energy as that's released when the reaction occurs in reverse. So this process is necessarily endothermic because we have to put that energy in. The next thing we're going to do is think about that work term. So work is negative force times distance, or negative force integrated against distance, and we can think about the work in a lot of different ways, but one key form of work we have is whenever there's gases in a chemical reaction, there's going to be a significant amount of work done just because any gas that's produced has to push up against the atmospheric pressure, that 14.7 pounds per square inch, or 1 atmosphere of external pressure. It's a lot of pressure. And so you actually have to do a pretty significant amount of work to push the surrounding gas out of the way and make room for some new gases that you might make. We can eliminate this problem by not changing our volume. So any change in work done associated with the external pressure is related to a change in volume of your system. If we don't allow any volume to be changed, then there will be no work done, and the change in energy will just be equal to the heat flow. That's the approach that's taken in the bomb calorimeter that we looked at in the previous set of notes. Now, as opposed to doing all of our reactions at constant volume, which would get rid of this work term, in chemistry and biology and in the environment, we generally do all of our reactions at constant pressure. So the natural thing we do then is we switch our variable from energy. Energy is very important, but it's not quite as convenient to work with at 1 atmosphere of pressure because we'd always have to be accounting for this little bit of work done from or by or on the surroundings. Therefore, we switch our thermodynamic variable from energy to enthalpy here. We define energy as E plus P times V. When we do that, that introduces this term here, which exactly counteracts the minus P delta V term from the work associated with the change in volume. And now we get this beautiful result that at constant pressure, the change in enthalpy of our system is equal to the heat flow. And that's sort of why, even though really energy is the thing we sort of care about, it feels more fundamental. When we're just talking informally, we always just talk about energy and not enthalpy. It turns out that it's a little bit more convenient to measure enthalpy in a chemical reaction and in biology and so forth here, because then we don't have to account for this P delta V work. When you think about enthalpy, though, you should just think about it as basically being energy. It's the same idea, just with this slight difference in definition to make it a little bit easier to work with. But anytime we're thinking about enthalpy, this variable H, you should really be thinking about energy in the energetics. If something is higher in energy, it's also higher in enthalpy. The units, again, are important. The units are the same, joules or kilojoules, just like the units for energy. Now that we have this relationship between the enthalpy change and the heat flow, we can use that to determine the enthalpy change of a chemical reaction. Okay, so we have that picture. We've switched the units of the picture from energy to enthalpy because that's going to let us know the heat absorbed or released. And then we're going to define the enthalpy change of a chemical reaction. So that's this here. Delta H of the reaction. We're going to define that to be equal to, because we have that relationship before, that delta H of the system is equal to Q at constant pressure, we can define the enthalpy of our reaction as the heat associated with that chemical reaction, where we need to get the sign of the heat correct, using like the reaction as the system, right? In this case, for a reaction like this, because it's set 571.6 kilojoules of energy released as heat, our sign on Q reaction would be negative, say, 571.6 kilojoules, right? That's because heat released means that we have negative heat change of our system. The system is losing energy as heat, while the surroundings are gaining that energy. Now, the denominator here is moles of reaction. So just like when we had chemical kinetics, we could define reaction rate in terms of like moles of reaction. To get this number that doesn't depend on the amount of stuff I have, the amount of moles, that just depends on how I write the reaction, I will take that heat flow in joules or kilojoules. This is just some amount of heat, and I divide it by the moles of the reaction that have occurred to make that heat flow. So that's the definition. And 1 mole of reaction is, in this case, for the way we've written this reaction, 1 mole of reaction is actually using 2 moles of H2, 1 mole of O2, and making 2 moles of water. It's the case then that if we want to use the moles of H2 that were consumed in order to determine the amount of, in order to determine delta H, I'm going to then need to sort of convert between moles of H2 and moles of reaction, just using the stoichiometry conversion factor. And again, heat released, I can also use that as my conversion factor and just do normal stoichiometry using the delta H as sort of the heat released. Again, in this case, exothermic, because that heat is released. So again, 2 important notes: you always need a balanced chemical equation, and phases are very important. If we made gaseous water rather than liquid water, we'd have a different delta H. So keep track of all of those things carefully. Now that we have a definition of delta H, we can introduce this idea of enthalpy arithmetic. So the idea here is just that because enthalpy is that state function, so delta H is always equal to HF minus HI, which in a chemical reaction is H of the products minus H of the reactants. Whenever I add reactions or multiply by 2 or something like that, I have a systematic change in delta H. So here are the rules. When I multiply a reaction by N, I multiply delta H by N. So if I had A goes to B and C goes to D, and I multiply it by 2, my delta H for this new reaction is 2 times delta H1 because I took this reaction, I'm multiplied all the coefficients by 2. If I reverse the reaction, that flips reactants and products, and so that changes the sign of delta H, so negative delta H1 there. If I add reactions, I add the delta H's. So if I take this new reaction, A plus C goes to B plus D. To do that, I get if I look at that, I can just add up reaction 1 and reaction 2 and get my final answer. A plus C goes to B plus D is delta H1 plus delta H2. Now, here's some examples. Take a second to try those out. Okay, so for A, I have my known reaction, and if I look at what I did, I took my known reaction and I multiplied everything by 1/2. So I took my known reaction, I multiplied everything by 1/2. To get the new reaction, I have half of everything. So my delta H reaction is going to be negative 189 kilojoules per mole times 1/2 as well. Now for B, if I look at B, I could start from here, but actually if I look at it, B is actually really close related to A. B, if I look at it, all I've done is flip reactants and products on reaction A. So in that case, I'm going to say, to get B, I just took A and flipped the reaction. So that means I need to change the sign of delta H. So this is going to be plus 94.5 kilojoules per mole. Because I've flipped reactants and products, that's rule number 2. Reverse reaction, change the sign of delta H. Because I've just changed reactants and products, which changes the sign of the delta there. With that key content out of the way, now we'll look at a bunch of different ways we can actually measure delta H of different reactions. Here's our first example where we're going to use calorimetry to measure the delta H of a chemical reaction. So we have the 1 gram of methane that combusted, and it caused the temperature of the calorimeter to increase from 20.013 to 26.267 degrees. We're also given the total heat capacity of the bomb and the water, 8.898 kilojoules per degree Celsius. So total heat capacity, that is this version of the heat equation. So we have Q is equal to C delta T. C here has these units of joules or kilojoules per degree Celsius. It's basically just a way, when we have multiple different materials, to incorporate them all into one big constant that lets us know the relationship between how much change in temperature causes how much heat to be absorbed or released. So yeah, total heat capacity is this capital C. In contrast to, in a lot of problems, we might be given, a mass of water is 100 grams, and then we know CS for water is 4.184 joules per gram degree Celsius. So just pay attention to that difference in units, specific heat capacity CS versus heat capacity capital C. The first things we're asked to calculate is the heat absorbed or released during this reaction. So that's usually the first thing we want to do from calorimetry. We're going to know a temperature change, and we can use that to figure out the heat. I would call this sort of the heat of the surroundings, or in this case, like the heat of the water or the calorimeter. And that, again, because we're given this capital C, that will be that top equation. Q is equal to C delta T, and so Q is equal to 8.898 joules per degree Celsius times TF minus TI is 26.267 minus 20.013. Gives us Q is 55.65 kilojoules, and this is again, maybe Q of the calorimeter would be a good subscript, and the idea here is that the calorimeter absorbed 55.65 kilojoules of heat. It gained all this energy as a result of the combustion. Now, the next step is to figure out delta H of the reaction. So the way we can do that is by, I'll write this as a separate step, is basically we're going to switch from Q of the surroundings to Q of the reaction. So again, what this means here is that Q of the reaction is equal to negative 55.65 kilojoules. Because, again, if the calorimeter absorbed heat, the reaction had to release all that heat. And this is what we expect. We're expecting, since the temperature increased, that this is an exothermic reaction. Exothermic reactions release heat and cause the surroundings to get warmer. Now, step 3 is going to be to use the definition. Delta H of a reaction is going to be equal to Q of the reaction over the moles of reaction. So to use this definition of delta H, all I need to do, I know the Q of the reaction. Moles of reaction is what I need to calculate. So I know the grams of methane, and I just need to convert that to moles of reaction. So in this case, I can start with 1.000 grams of CH4 times, I have grams, I need to then get to moles of methane. The conversion factor there is 1 mole of methane is equal to 16.04 grams. Then the next conversion factor I need to do is convert to moles of reaction. So in this case, that's just a 1-to-1 ratio, because according to the balance coefficients here, each mole of methane, the reaction is written here. This whole thing we should view as 1 mole of reaction. And the coefficient on methane is 1. So it's 1 mole of the reaction is equal to 1 mole of methane. But sometimes we'll do problems where, again, if we were measuring the oxygen, we would have 2 moles of oxygen is equal to 1 mole of reaction. So you should always pay attention to that factor. That gives me 0.06234 moles of reaction. And now the final step will just be to plug back into the definition, take Q over the moles to get delta H of the reaction. So plugging in, Q of the reaction is negative 55.65 kilojoules divided by 0.06234 moles of the reaction, and we get a final delta H of negative 892.6 kilojoules per mole. Again, we know that makes sense because it's a negative here, exothermic reaction causing the surroundings to get warmer. In order to use the next approach to calculate the enthalpy of reaction, we need to define an enthalpy of formation. So the enthalpy of formation is defined as delta H of reaction for the reaction that forms 1 mole of a compound from its elements in their standard states. The standard states are the stable form of that element at atmospheric pressure and room temperature. So the standard state of different elements, we can sort of see that in the table down below if we take a look. Br is a diatomic compound. It exists as the molecule Br2, and it's a liquid at normal 1 atmosphere pressure and 25 Celsius. So its delta H of formation is 0 because the reaction we're thinking about then is Br2 liquid goes to Br2 liquid. It's delta H of that reaction that is the delta H of formation. And since this reaction is nothing, it's just no change, delta H of formation for the pure elements in their standard states at room temperature are 0. So the same thing for some of our other compounds from the table. Graphite is the sort of standard stable form of carbon at 0 or at 25 Celsius and 1 atmosphere. Same for H2 gas. Same for N2 gas down here. All the elements in their standard states are a delta H of formation of 0. Other details, the circle here that's in the definition and here, that circle represents 1 atmosphere of pressure is the standard state pressure that we're thinking about. That makes a small difference for these enthalpies. It's important to specify exactly what conditions we're measuring things under. We'll see later, though, that for other things, this circle makes a much bigger difference. So on this table now, we have a delta H of formation for each compound. And what's so powerful now is that we can use the idea that delta H of a reaction is just products minus reactants to calculate delta H. So delta H of the reaction is going to be equal to H of the products minus H of the reactants. And a small table like this with a certain number of entries will let us write and determine the enthalpy change for any reaction that involves these compounds. So rather than needing a separate delta H for every reaction, if we can get a delta H of formation, we can use this table to calculate delta H for any reaction we care about. This gives a way of understanding that. We can think about it as sort of adding up those individual steps. So we could think about it as CH4 plus O2, first breaking CH4 into the elements, graphite and 2H2, and using this as basically our 0 point of energy, since these are the elements in their standard states, and then forming our CO2, forming our H2O. So in that way, we could do this sort of Hess's law approach, where we add up the delta H for each step, flipping reactions and things like that. The final result, though, is just products minus reactants. So this type of formula is one that you could get on your equation sheet. It looks sort of intimidating, right? But all this is saying is that we take the products and we multiply delta H by the number of moles for each, and then we subtract off the reactants, delta H of formation for each, times the number of moles. Again, because the 2 moles is going to have twice the energy and twice the enthalpy of just a single mole. So here's that example from the table. CO2 has an enthalpy of formation of negative 393.5. So to do this reaction, I'm going to take delta H of CO2 times 1, because the coefficient is 1, plus 2 times the delta H of formation of liquid water, which is negative 285.8. Then I subtract off the reactants, right? So that's going to be CH4. The delta H of formation for CH4 is negative 74.81, plus the other one here, which I didn't include on this slide, is O2, because O2 is an element in its standard state, so its heat of formation is 0 by default there. Then when I do that, I can get my overall delta H of the reaction. So doing that, products minus reactants, gets me delta H of the reaction is negative 890.29. This agrees pretty closely with the answer we got from our calorimetry experiment. And in general, this is always, one of the most precise ways of calculating delta H of the reaction. Next, we have a few exercises using those heats of formation. For this one, which of the following reactions is the heat of formation reaction of gaseous ammonia? That just relies on the definition. The definition is that delta HF is basically what we want to do is we want to form 1 mole from the elements in their standard states. So that lets us rule out something like this. Heat of formation reaction of gaseous ammonia, I need to form only 1 mole. And that also rules out this. I want gaseous ammonia, so it's going to be this B reaction. A half mole of N2 plus 3 halves mole of H2 gives us 1 mole of NH3. So delta H of that reaction is equal to the delta H of formation for NH3. Here's the next exercise. To solve this, I just need to apply the definition. I can use that fancy equation, but really just a more straightforward delta H is going to be equal to the products minus the reactants. That will work as long as I remember to multiply by moles where necessary. So the products here are 4NO. So I can look at NO, and I do have the right phase there, 4NO gas, so 4 times 90.25, plus the other one is 6H2O gas, so I do need to use the gas and not liquid, so times 6, plus 6 times negative 241.82, minus the reactants here I'm going to have are 4NH3, so 4 times my NH3 is in the gas phase, so I need NH3 gas, negative 46.11, plus O2 is in the table, but since it's an element in its standard state, we do know that's going to be 0 also. So 5 times 0 can cut that one out basically, and then get our final delta H. That gives us our final delta H of negative 905.48. So for this problem, we are going to use Hess's law. The idea here is we choose how to use each reaction, whether we need to flip it or multiply by 3, or however we want to use the given reactions. And then the final step is going to be to add those individual steps up to get the overall reaction. So let's see how that works. In this case, it's not difficult to know where to start. We could actually start anywhere. But if I look at my 3CH2, my question I want to ask is, where am I going to get 3 moles of CH2 as a reactant? I can see based on the given reactions that the way I should do that is by taking this reaction 1, that's the only one with CH2 in it, and I multiply that by 3. So I'm going to multiply all of that by 3, and that will get me 3 moles of CH2H2 as a reactant. Now for the C6H6 as a product, I can do that by just flipping this reaction. So I'm going to flip this reaction, which is going to mean, basically multiplying it by -1. Let's check that that works out. So the idea is I'm going to take 3 times this reaction, flip this reaction, add those 2 up, and hopefully I get the reaction here that I want. So for the first one, so I've written all of that out, multiplying this first reaction by 3. So delta H for this is now -3898.2, multiplying the delta H for reaction 1 times 3. And for this one here, I've flipped reactants and products, so delta H went from negative to positive. Now let's check that when I add these reactions up, everything works out. So when I add them up, just like we did in sort of the kinetics part of the class, if I look, I have 15 halves O2 on both sides. That cancels out. I have 6 CO2. That cancels out. And I have 3 H2O liquid. That cancels out. So this has verified that I've done everything right. And my final reaction is 3C2H2 gas goes to, I'll just write forward arrow, goes to C6H6 liquid. And this last step was sort of adding the reactions. So the final thing I need to do is add these 2 delta H's. So I'm going to get -3898.2. When I do that final step, adding the delta H's, when I add the reactions, I get -630.8 kilojoules per mole. So this is a Hess's law approach where we can take delta H for some reactions and use it to get delta H for a related reaction. Here's that same step shown out on the slide here. Here's our next exercise, just parts A and C, omitting part B. For any of this sort of problem where you're getting delta H from the table, the equation is the moles of product times delta H of each product minus the moles of reactant times the delta H of each reactant. So in this case, that looks like this. So the general equation looks like this. We're going to take the delta H of COCl2, -108.3, times the coefficient is just 1, so just one of those, and then we subtract off the reactants, which is delta HF of CO from the table, -110.52, plus delta HF of Cl2. If you look, then Cl2 isn't in the table, so the reason that's okay is that Cl2 is the standard state of the chlorine element. And so remember, delta HF for an element in its standard state is exactly 0. So that we can just plug in as 0 and get our final answer. And so our final answer is 2.22 kilojoules per mole. With proper rounding, I guess we should round that to 2.2 kilojoules per mole, because we only get to keep to the tenths place here, since this one is only known to the tenths place. Again, the unit kilojoules per mole right out of the table. This is a little bit of a trickier example, since we're not just calculating the heat of the reaction. We're given the heat of the reaction, and we need to know the enthalpy of formation for, in this case, benzene, C6H6 liquid. The approach, though, is the same. We're still going to use the fact that delta H of the reaction is equal to, we do our products minus reactants, so CO2 is in the table here, negative, that's going to be 6 times -393.51, plus 3 water liquid, so I need to get H2O liquid, which is -285.83. Then when I go to the reactants, I have C6H6 liquid. So the whole goal is to calculate the value of that heat of formation. So let's just call that our x. And there's only 1 mole of it, so it's just going to be minus x here. Plus, if I look at the other things here, 15 halves O2. O2 is an element at standard state, so this is just 15 halves times 0, all just 0 there. Delta H of the reaction, of course, that is the negative 3267.4 kilojoules per mole that were given as the heat of combustion, because this is the combustion reaction for benzene. So simplifying, I get this equation, then I just need to, I don't know, I could add this over to the other hand side. Maybe I'll do that. I'll add the negative 3218.55 to both sides. When I do that, I get negative 48.85 is equal to negative x. When I do that, I get negative x is 48.85, so therefore x is positive 48.85 kilojoules per mole. Always remember your units. And one of the nice things of this problem is it sort of tells us how we actually find heats of formation in reality. While it's hard to actually do the heat of formation reaction, once we do this combustion reaction, we can take the other known heats of formation and get the heat of formation of some new compound that we make, and then enter it into our table and use it in any other reaction we care about. We now have one final way to get the enthalpy of a chemical reaction, and that's by using this estimate from bond dissociation energies. So the definition of bond dissociation energy is it's the energy required to break a chemical bond. So for example here, H2 goes to 2H. If we think about the Lewis structures of both involved, that's 2 hydrogens connected by that single bond. And when we have 2 hydrogen atoms in the gas phase, they each have, just a single electron, that ground state hydrogen atom, and no bonds in the products here. So if I calculate delta E or delta H of this reaction, I'm going to get the amount of energy it takes to break that bond. In this case, it's quite a lot, 436 kilojoules per mole. And then what we can do is make a table of the energy in each type of bond. So what we'll do here is our first entry in our table will be that an HH bond has a bond energy of 436 kilojoules per mole. Now we do this for all sorts of different reactions, all sorts of different bonds, and get a rough average of how much energy it takes to break each type of bond. This then lets us give a really quick estimate for the enthalpy of a reaction, and it also really connects the enthalpy to the meaning. When we break bonds, we have to put energy in to overcome, the strength of that bond. Bonds form because they are lower in energy than the free atoms that they start with, connecting all the way back to the beginning of the class when we did Lewis structures and our different bonding theories. So here's that resulting table, the result of, thousands of, person years of work studying all sorts of different chemical reactions. On average, this is the energy associated with each type of chemical bond. We can see, just like when we did Lewis structures and molecular orbital theory, a double bond between atoms is going to be a larger bond energy than a single bond. So CC double bond, 611, versus CC single bond, 348. A triple bond, again, even more energy, 837 kilojoules per mole. And this is the energy that's required to break the bond, the energy that we need to put in to separate the atoms. There's that nice tie-in with bond length as well. Single bonds are the longest and the weakest bonds. Double bonds are shorter and stronger. Triple bonds even shorter and even stronger still. So when we think about this bond energy, this lets us use another thermodynamic cycle to calculate delta H of a reaction. And here now, as opposed to using the elements in their standard states as our reference, we're going to actually use the free atoms floating around on their own with no bonds as the sort of reference state that we're going to take. And so if I think about a reaction like this, H2 plus F2 goes to 2HF. To go from reactants to products, I can think about first breaking the bonds in the reactants. I have to put energy in to break those bonds. So it's, the bond energy of HH plus the bond energy of FF. That's the energy I put in. And then when I make the products, I'm going to form 2 HF single bonds. And so that's the energy that's going to be released. So minus 2 times the HF bond energy. And that gives me my delta H of reaction. The overall approximation that we're making here is we're going to say delta H of the reaction is the bonds broken in our reactants So I add up all the energy of the bonds that I'm going to break from my reactants, and I subtract off the bonds that I'm going to form in the products. Note that this is reverse of how we normally have it, where it's products minus reactants, but that's because the bond energy is the energy it takes to break the bond, and so that sort of flips reactants and products. Anytime we are breaking a bond, that's going to make delta H more positive, more endothermic as a reaction. Anytime we're forming bonds, that makes a reaction more exothermic. That's going to release energy. In this case, this is a highly exothermic reaction with delta H is negative 543. That's because the bonds we're forming are so much stronger than the bonds we're breaking. Especially, we can see that this FF single bond is incredibly weak, and so it's incredibly favorable and beneficial to break that bond and instead make this incredibly strong HF single bond, actually the strongest single bond on the entire periodic table. So again, when we do this, we get both an estimate of delta H, but also really good understanding of why a reaction would be exothermic or endothermic. It's going to be exothermic if we form strong bonds in the products. A reaction is endothermic if, the bonds that we break are a lot stronger than the bonds that we make. So here's the approach for estimating using bond energies. The first thing we need to do is have the Lewis structures. So we need to write out the Lewis structures of our reactants and products. Then once we have that, we can figure out which bonds we're going to break in the reactant. So in this case, because it's 1 mole of CH4, it's 4 CH bonds that we're breaking. 2 moles of O2, so that's 2 OO double bonds that we have to break. To form the products, then, I get 1 mole of CO2, which has 2 CO double bonds. So I'm forming 2 CO double bonds, get the number off of the table. And I'm forming, each water has 2 OH single bonds, and there's 2 moles of that, so 4 OH single bonds. That gives me my total making energy, all the bonds that I'm forming. Then I take the bonds that I break, subtract the bonds that I form, and I get an estimate of negative 798 kilojoules per mole for this reaction. So very exothermic, and again, this gives us that information about why it would be exothermic. If I had to pick one real reason, OO is pretty unstable. The OO double bond is pretty strong, but look at how much weaker it is compared to the CO double bonds that I'm going to form. Each time I take an OO double bond and replace it with a CO double bond, it's making the bond go from 500 kilojoules per mole to 800. So it's releasing 300 kilojoules of energy every time I do this. And that's the general reason that combustion reactions are so exothermic, so favorable, and are able to release so much energy, is because we're taking, the relatively weak double bond in oxygen and replacing it for this incredibly strong CO double bond in carbon dioxide. The same thing for water. CH has moderately strong single bonds, but OH bonds are even a little bit stronger, so that makes this reaction even more exothermic. All the bonds that we're forming are stronger than the bonds we're breaking, so highly exothermic reaction that we can use to do a lot of useful things in terms of power plants and heating your food on your stove. All sorts of things because of how much energy we release when we form the strong bonds in carbon dioxide and water. So here's our final example. See if you can estimate the enthalpy change of this reaction using the bond dissociation energy table. So our first thing that we need are the Lewis structures of each of these. I'll write those out here. This is good review for the final exam. The first Lewis structure here is methanol. And again, if we look at the skeleton structure, CH3OH, the skeleton structure is here. Then we add our 2 lone pairs on oxygen to get oxygen to a complete octet. That works out. This is one of those organic molecules where, remember that everyone typically has a formal charge of 0. And so oxygen is always making 2 bonds and has 2 lone pairs in this type of structure. So this all checks out. Oxygen brought 6 electrons and has 6 electrons assigned to it according to formal charge. We can also just count the total valence electrons: 2, 4, 6, 8, 10, 12, 14. So 14 valence electrons, and carbon has 2, 4, 6, 8, full octet, oxygen 2, 4, 6, 8, complete octet. So this is the correct Lewis structure for methanol. Those other Lewis structures were all on the previous slide, but here they are for reference. So here it is, oxygen with those proper 2 lone pairs on each, carbon dioxide, and water. Then the equation, we're going to take the bonds broken in the reactants and subtract off the bonds that are formed in the products. A lot of bonds to count up here, but I'll try to do that here. So we've got 1, 2, 3 CH bonds times 2, so we're going to break 6 CH bonds. Plus we've got 2 CO bonds, plus 2 OH bonds, plus 3 O double bond O bonds. That's all the bonds we're breaking off in the reactants, and the bonds that we're forming in the products I'll write below here. So we subtract off the bonds that we form, 2 moles of CO2, so we're going to form 4 CO double bonds. Plus we're going to form 4 moles of water, which works out to 8 of those OH double bond, OH single bonds. And when we plug in the values for each of these bonds from the table, we'll get the correct solution. Now, if you wanted to, you could net out the things in common on both sides. In this case, it's only 2 OH bonds, right? I could net this out and switch this to 6. Because again, I had 2 OH bonds to start with. I have 8 in the product, so I'm net forming 6 OH bonds. In this case, I don't know that that makes much sense because it's only a small difference in amount of work. Then plug in, just get the appropriate number off of the table with all of our reactants here, breaking all of these bonds, forming these strong bonds in the products. We get a total delta H of negative 1291 kilojoules per mole. Again, this is another combustion reaction that's quite exothermic because of the strong bonds in CO2 and H2O. Forming strong bonds means that it's going to be an exothermic reaction, releasing quite a lot of energy as heat. When you're doing this, remember that this parenthesis here matters a lot because you're subtracting off this whole quantity in parentheses. So you definitely need to take all of your products here and put them in parentheses. So that's all of the new content on thermochemistry. A lot of review slides here. The main content is the 4 ways we can calculate delta H of the reaction, where delta H of the reaction is the enthalpy of products minus reactants in units of kilojoules per mole of reaction. One way is using calorimetry, where we have these key equations. Q is C delta T, or Q is MCS delta T, where this uses the specific heat capacity and the mass, or just the total heat capacity. Then the reason we use enthalpy rather than energy is that at constant pressure, delta H is equal to Q of the system, where Q is in joules or kilojoules. Then what this lets us do is calculate delta H of the reaction using calorimetry, where we can take Q from the perspective of the reaction. So if the reaction is releasing heat, we would have a negative Q for the reaction. If the reaction is absorbing heat, we'd have a positive Q for the reaction, and divide it by the moles of reaction. Moles of reaction works just like when we did kinetics. We write whatever the balanced reaction is, and we say that whole thing is equal to 1 mole of reaction. So as an example, if consuming 2 moles of A caused 17.5 kilojoules of heat to be released, we could calculate delta H of the reaction as follows. First, convert moles of A to moles of reaction. So 2 moles of A, or 4 moles of A is equal to 1 mole of reaction from the coefficients here. And so 2 moles of A is equal to 2 times 1 over 4. 1 mole of reaction for every 4 moles of A is equal to 0.5 moles of reaction. That makes sense. If I was going to have 1 mole of reaction, I would have needed to use up 4 moles of A. Then I take delta H of reaction as Q divided by moles of reaction. So in this case, negative 17.5 kilojoules because the heat was released, divided by 0.5 moles of reaction, gives me 35 kilojoules per mole, or negative 35 kilojoules per mole as my delta H. Heat is released, so Q of the reaction is negative, and the reaction is exothermic. So you can always double check based on whether the temperature went up of the surroundings. If the temperature of the water went up, that's a sign that the reaction is exothermic. If the temperature of the solution went down, that's a sign that it's endothermic, that heat is going to be absorbed as the reaction progresses. This is also where we use that sort of first law of thermodynamics. Negative Q of the system, or Q of the reaction, is equal to positive Q of the surroundings, or Q of the water. Some other methods, we have Hess's law, the idea that when we add reactions, we add delta H's. And the other two rules to remember: when we reverse a reaction, we get negative delta H, multiply by N, multiply the delta H by N. Pretty simple. When you're applying this method, you sort of think about how you're going to use each reaction. And, I might take 2 times reaction 1 and take -3 times reaction number 2. I just want to basically rearrange the given equations in order that I can add them all up and get the reaction that I want. Method number 3 is with formation enthalpies. This is probably the easiest one. Just take the products times their moles minus the reactants times their moles. This is also going to apply to any of our other thermodynamic variables and thermodynamic functions that we'll look at next time, which it will include S for entropy and G for free energy. It's always products minus reactants. Standard state is introduced here. Remember that that's 1 atmosphere of pressure for gases, 1 molar for aqueous species, and Q is equal to 1 for any reaction from the equilibrium unit. The standard state of an element is its most stable form at 25 Celsius and 1 atmosphere. And remember, therefore, delta H of formation for any element in their standard state is equal to 0. I'm trying to rewrite that, but it's actually right up here as the key point up above here. For an element in its standard state, delta H of formation is equal to 0. So that applies to, O2 gas, carbon, graphite, any of those elements in their most stable form at room temperature and 1 atmosphere. The last one here is bond dissociation enthalpies. So using the Lewis structures, we can take the total breaking energy, the breaking total bonds broken in the reactants, subtract off the total bonds formed in the products, and use that as our estimate of delta H of the reaction. So this is the one that's different than the normal case. In this case, it's reactants minus products. Breaking bonds requires us to put energy in as heat. Forming bonds causes energy to be released as heat. So the signs do all make sense here. Whenever we form a bond, that's going to cause energy to be released, and will make the reaction more exothermic. Whenever we have to break a bond, that's going to have a tendency to make the reaction more endothermic. So this also lets us estimate the sign of delta H for reactions. So something like this: O2 gas goes to 2O. In this case, we're breaking only one OO double bond and forming no bonds, so we know that this has to be an endothermic reaction because breaking bonds causes some input of energy. So we'll have, in this case, if we did the actual math, we'd get 498 minus 0. We break 1 bond in the reactants and we form no bonds in the product, so we get plus 498 as the delta H. But again, even without the numbers, you can say that since we're just breaking a bond and forming no bonds, it will have to be endothermic and cause energy needs to be put in to make this reaction proceed.